All right, so today we're going to look at 7.3, which is on solving trig equations graphically. So we've done a little bit with solving trig equations, but they've always been basic equations on the calculator, like sine of x equals 0.6. You put it in y1, y2, you find an intersect. What we're going to start to look at, and we'll practice a basic one, but what we're eventually going to start to look at is something like that. Okay, that's a much more complicated trig function. Not something we'd ever sketch by hand, but it's got things that are squared, things that aren't squared, and we're mixing multiple trig functions in the equation. So one important thing we got to talk about is period. How do you find the period of a complex trig expression, where complex means there's multiple trig expressions and possibly raised to different powers? We'll talk about that. Okay, so just a reminder what it means to find all solutions to a problem, and we've done this many times. First thing you have to do is find all solutions in one cycle. So that requires us to know the two formulas, pi over b and 2 pi over b. So 2 pi over b is used for the sine, cosine, secant, and cosecant. Pi over b, tangent and cotangent. Knowing how to find the period of the basic trig functions is going to help you find the period of the complex ones. All right, so we find all the answers that are in one period, and then we put each one of those answers down, and we put plus the period times n, because those answers are going to repeat every cycle. So any question on that idea? The only time you don't need to find all solutions is if they give you directions and say, find all solutions between 0 and 2 pi. That's different. You're just going to find the ones that are between 0 and 2 pi. Nothing smaller, nothing bigger. So let's try this one. And it does say all. So keep that in mind. All right, how would I do this on the calculator? What would be my first step? Yep, Lens. What's that? So if I was solving this problem without any directions, yes, I would do inverse sine on both sides. I would not use a graphical approach to do this problem, but this whole lesson is about graphing. So we are going to use a graphical approach.
You would just type in sine of x on the y.
Okay, so put sine of x on y1. Yep.
And then you just put 0.8 on y2.
On y2, okay. Okay, we always got to set the window. Don't ever go to graph without setting the window. Can somebody else tell me what I should set for an x min and an x max? Yep, Layla?
0
Right. This is a sine function. Nothing complex about it. Just a trig function to the first power. When we want to find the period of it, it's 2 pi over b, and in this case, b is 1. So to get one cycle, we're going to go 0 to 2 pi. Now the highest and lowest, we got to worry about 1 and -1. We're fine. Okay, we got a little bit extra. So we'll graph it. And Craig, what do I do now that I've graphed it?
Find when the line, when the sin of x touches 0.8.
Yep, and how would we do that on here?
I believe it's trace.
So okay, I can press trace.
And you click the blue line and then the red line when they intersect with one another.
All right, how do I click the blue line? Because, well, now I just messed it up. Let me fix my window again. I messed up my window a little bit, but it's okay. It still works. So if I press trace and then I just hit enter, that didn't work. Yep.
Second trace.
Second trace. Then we go to intersect. Now we can do blue and the red. So that's my first answer. Okay, let's do it again. Second calc intersect. There's my second answer. And let's round those to 3 decimal places. So we've got 0.927. We've got 2.214. And what do I need to do to finish writing those answers? Nick?
Add plus 2 pi n.
Right, add plus 2 pi n. Okay, so nothing new there. We've done that before. I don't think it's the best way to do that. I would do it with the inverse sign and use the ASTC diagram to get the other answer. Right, but again, this is more of a graphing section. So, all right, any questions on that one? All right. So when we set any equation equal to 0, not just a trig equation, any equation, remember that means you are finding the roots or finding the zeros. So that's just a reminder about what it means when you set an equation equal to 0 and solve. You're finding the roots. So if we are looking at a periodic function like sine, cosine, tangent, secant, cosecant, or cotangent, and you take that periodic function and put it into an equation, well, now you have a periodic equation. So a periodic function is just something like that. Sine x, that's a periodic function. A periodic equation is when you take sine x, put an equal sign, and then put a number on the other side. That is a periodic equation. Any question on the difference between a function and an equation? Equation has an equal sign with a left and a right. A function does not. It's just like square root. That's a function. Square root's not periodic, okay, but the trig ones are. All right, so let's say that we're solving a problem like the last one we did. It had 2 solutions. We could have 2 solutions, we could have 3 solutions, we could have as many solutions as we want. The more solutions we have, the longer it's going to take because we've got to do second calc intersect on every single one of them. So remember, the idea for writing all the different solutions is you take each solution that you find in one cycle, and then you put plus the period times n on each one. Right, so just kind of summarizing what we've done before. And remember that n has to be what kind of number? Lens?
Would have to be positive.
No, it doesn't have to be positive. It tells you right on the board what n has to be. What does n have to be? Yeah?
All real numbers.
Nope. That doesn't say all real numbers. What does that say? I think we talked about that symbol very first day of class. Maybe second day. So it's very important we understand why we're putting period times n. You have to know why we're doing that. What does that n mean? Yep.
Is it anything but 0?
No, it could be 0. 0 is okay. That's the symbol for integers. N is an integer. So when you put plus the period times n, you're saying that you can add or subtract integer multiples to your answer to get answers in other cycles. Any questions on that? Okay, you have to write down every answer that's in one cycle. If you don't write all the answers in one cycle, that's not correct. You have to write all the answers in one cycle. All right, so now we've got to look at how do we find the period of something that is more complicated. Okay, something like sines and cosines and tangents all mixed together and raising to different powers. Well, the first thing is you have to find the period of each periodic term. So if we look at the problem that we're about to do, how many terms are on the left side? Yep. No. How many terms on the left side? Ethan? 3. How many periodic terms? 2. So, can you tell me what the 2 periodic terms are?
2 cosine squared t and sine t.
Yep, those are the 2 periodic terms. So when I say find the period of everything that's periodic, I mean the trig functions. 1 is a constant. That doesn't have a period to it. So find the period of each periodic term. And then once you find those, the period of the entire problem is the least common multiple of the individual periods. Okay, least common multiple. So remember, the least common multiple is a number that everything basically divides into. So if I said, what's the least common multiple of 2 and 3? It'd be 6. Because 6 divided by 2 doesn't have a remainder. 6 divided by 3 also doesn't have a remainder. And 6 is a multiple of 2 and of 3. All right, so let's take a look at this one. And let's start with sine t. What's the period of sine t? Yep.
2 pi.
2 pi. Okay. So that has a period of 2 pi. We've never looked at cosine squared. Right. Well, let's graph it and see if we can figure out the period of cosine squared. Okay, there's a difference between how you write a trig function on paper and how it looks on the calculator. This is how you have to type cosine squared in on the calculator. On paper, they write the exponent in between the argument and the trig function. That's just how they do it. This means exactly the same thing as that. Be careful when you square it that you don't do something like this. That is not the same thing in y1 and y2. This means take the x value, square it, then take the cosine. This means take the cosine of the x value first, and then square the answer after. All right, I'm going to set my window from 0 to 2 pi. Graph that's cosine squared. And I want to see if I can look at that and figure out the period. So this is 0. That's 2 pi. Anyone think they can see the period of cosine squared? Yeah.
0 to pi over 2.
So you're saying this is one complete cycle right there? Yeah.
0 to pi.
0 to pi. There's 2 cycles in that picture. There's 1. There's 2. So there's 2 full cycles in that picture. And our window is 0 to 2 pi. So that means this is pi, and that is the end of one cycle. Okay, so the period of cosine squared is pi. What's the least common multiple of 1 pi and 2 pi? How about Marin? What's the least common multiple of 1 pi and 2 pi? A least common multiple can't be smaller than any of its individual values that we're using to figure it out. So like if I said, what's the least common multiple of 5 and 7? It couldn't be 6, because 6 is smaller than one of the things I'm trying to use to figure it out.
So
2 pi, yeah. So remember, multiples of pi, right? Pi, 2 pi, 3 pi, 4 pi. Multiples of 2 pi. 2 pi, 4 pi, 6 pi, 8 pi. So we're trying to look at those lists and find the smallest number that's in both lists. 2 pi is the smallest multiple in both lists, so it's the least common multiple. That's important because it tells us what to set the window at, and it tells us what we need to add on the end of every answer we find. If we can't figure this out, then we're going to be stuck at this step. But that's how you do it. All right, so I've got my least common multiple. What do you think I'm going to do next?
Would your window be like 0 to 2 pi?
Okay, yeah, we can set a window. Let's do that. So 0 to 2 pi, all right, I'm already good with my window. So I'm 0 to 2 pi. Might have to adjust the y min and y max. We'll see when we get to that. Actually, you know what, let's just do it now. Let's do -3 to 3. See if that's enough. Okay, what else do I do? Anyways, what do I do next? Well, we're going to be solving for roots, so we want to get everything on one side and 0 on the other. So that's actually good the way it is. Just plug it in. Yep. So let's put 2 cosine squared x plus sine x plus 1. Now, this isn't going to look like a sine or a cosine wave because it's more complicated. It's going to have a pattern to it, but it's not going to be just a nice simple wave. My y max is a little too low, so I am going to fix that. Let's put the y max at 4, and that's good. That is a picture of the graph. So when you draw one cycle properly, it should always begin and end at the same y value. So that way, if I were to take that picture, trace it, and line it up next to it, that should be perfect and tell me what the next cycle looks like. Okay? So that's what this graph looks like. It's that purple section repeating over and over. Okay? And we're trying to find where it equals 0. So what does that mean I'm looking for in that graph? Rush? Where the line touches the x-axis, yeah. So I'm going to try to calculate that. Now that I can see the entire graph, I might want to zoom in a little bit. Why might I want to zoom in right over here? Yeah?
To see if it goes below more than one.
Right, that's the question. Does it go below it? So I could zoom in and try to look at it. It's still kind of hard to see. The other thing I could do is I could just calculate the minimum. If the minimum is a negative number, then I know it goes below and comes back. If the minimum is 0, then I know it touches the axis and doesn't go under it. If the minimum is positive, then I know it never actually touches this axis if I kept zooming in. So let's figure out where the minimum is. Okay, the minimum is at 0. So that tells me the graph never actually goes under the axis and comes back up, which means it touches it one time. And that is where it touches it. 4.71, that is your answer. If you did second calc 0, that's going to give you, should give you the same thing. Yeah, 4.71. Okay, so is any question why I did the minimum there? It's kind of important just to check it out. Sometimes you could spend all day zooming in and then you realize it just barely goes under it. But if you had done the minimum, you would have been able to find that a lot faster. Okay, so we get 4.71. And what else do I need to do there? Right? Plus the period times n. So the next time you're going to see this answer is right there, and that's exactly 2 pi units later. And it's going to be every 2 pi units later and earlier. Since n is an integer, it could be a negative number, and that would represent answers going the other way as well. Questions on that one? All right. So we don't want to have to worry about, well, what if it's cosine squared? What's the period? What if it's cosine cubed? What if it's cosine to the 5th? Graphing it every time and trying to figure it out, that's going to add a lot of time to the problem. So we're going to come up with a rule, and it's really going to be based around even and odd exponents. It's going to be a very simple rule to figure out the period all of the time. This one, we don't have to worry about that because we have 2 trig functions that we're familiar with. No powers this time, so I'm not going to explain that rule yet, but I will. Okay. What would we do first here to get this problem looking kind of like the last one? Yeah?
Put everything on one side or
Yeah. Let's put everything on one side. If we want to continue what we've been doing, which is finding roots, you got to get it equal to 0. If you want to find intersects, then you don't. You could do a y1 and a y2 and see where they cross. But my goal is to put everything on one side so I can show you what the actual trig function looks like, not 2 separate functions crossing each other. So, Lens, how would I do that?
Would you subtract the n of x on both sides?
You could subtract the tangent of x, or you could subtract the 3 cosine x. It doesn't matter. Okay, and if you're wondering, well, why wouldn't it matter? Because if you had subtracted the 3 cosine x, then you would have had a negative 3 instead of a positive 3. Yes, it would change the picture of the graph, but it would not change any of the x-intercepts. It's kind of like if you had a parabola, just to give you a really simple example. If you put everything on one side, you might get a picture like that. If you had put everything on the other side, you might have gotten a picture like that. So yes, it does change. It does change what the graph looks like, but it doesn't change the x-intercepts. You just got to put everything on one side. Okay, what's the period of cosine x? Yep. 2 pi. What's the period of tangent x? Yep. Pi. What's the least common, this comes up a lot, what's the least common multiple of 1 pi and 2 pi? 2 pi. Okay. So now I know what to set my window to. I also know what to add on the end of every answer that I find. Okay. Let's put that in Graphically. So we've got 3 cosine x minus tan x. Window is already 0. I must have changed. Oh, I zoomed in. That's why everything is different. So let's put it back on 0 to 2 pi. Let's fix the y min and max. Let's do -5 to 5. Not worried about going up and down forever because I know tangent has vertical asymptotes. So I'm never going to see the top and the bottom of this graph. And that is one cycle of your graph. So it's that pattern repeated over and over. Now, sometimes if you break a cycle into pieces like we did here, it's kind of hard to visualize what it really looks like. Did that all stay? No, it didn't stay together. So let's take that, group that all together. And what this graph really looks like is that. So it's this piece over here could have been connected to this piece over here. So if I had found a better window, I could have shown you one cycle by looking at those two pieces. That's what it really is. But because I broke the cycle up, my graph makes it look like it's 3 separate pieces. That's fine. Either way, how many times does it cross the x-axis per cycle? Yep, 2. Yep. So we're just going to find each crossing. Second calc. This time there is no doubt that it goes right through the axis. I don't have to do second calc minimum. I can see clearly it goes right through it. So we've got 2.13. And let's get the other one. 1.29. And don't forget to put the plus 2 pi in. Now, what would you put on the end if you were doing it in degrees? You would be putting plus 2 pi n in this problem. That's?
Would you have to turn like 2 pi into degrees?
Yeah, and what would that be?
360.
360, yep. So if you do this problem in degrees, you would use 360 n. You'd have to set your window 0 to 360, and you change your answer. This would be different, and those would be different. But you can do it in degrees if it asks you to. If it doesn't, then use radians. All right, so now we've got sine cubed. At this point, we really want to figure out a pattern before we do this problem now for finding the periods in general. So let's look at this. These can all be categorized using the same formula. Sine, cosine, secant, and cosecant to an even power. And tangent and cotangent to any power. These all use the formula pi over b. Pi over b. Now, what's the other formula that we've used besides pi over b. Yeah.
2 pi over b.
2 pi over b. Well, what cases are left? What case do you think 2 pi over b is going to cover? Yeah.
Odd exponents for sine, secant, cosecant, and oh yeah, cosine.
Cosine, yeah. So it's just the odd powers for sine, cosine, secant, cosecant. So that covers everything. So now we don't have to play around trying to graph something and say, okay, it looks like this is the period. We can find the period of any trig function that we've studied so far to any integer power. You won't be raising trig functions to decimal powers. That's not something we'll get into. So now I'll keep that up, and let's look back at the last problem and see if we can use this to help us figure it out. Okay, let's start with sine cubed, 2x. What is the formula to figure out the period of sine cubed? Just the formula, that's all I want. Nick?
2 pi over b.
It's 2 pi over b. And can you tell me what b is in this case? 2. Yep. So what's the period of sine cubed?
Pi.
Pi. Sine cubed 2x. Sorry. Period is pi. What's the period of cosine x? 2. Two pi, yeah, 2 pi. So we get pi for the period of sine cubed 2x, 2 pi for the period of cosine x. What's the least common multiple of pi and 2 pi? Yeah, 2 pi. Okay, so now set your window, plug all that in, and find your answers. It's already equal to 0, so I don't have to rearrange it to make that happen. So we're going to type in 3 sine 2x cubed. That's how you do it. That's 3 sine cubed 2x minus 2 cosine x. And remember, we're looking for how many times it crosses the x-axis. Check your window. We're good. 0 to 2 pi. Okay, let's take a look at that. And how many times does it look like that graph crosses the x-axis? Yeah? 6 times. So yeah, we do have, that's kind of a lot. We'd have to do second calc 0 6 different times. Probably won't give you one with that many like on a test, but I'm just showing you, you can get that. And I already have them all done up. So you're gonna get 0.5, 1.25, 1.57, 1.89, 2.65, and 4.71. And what should we make sure that we add on all of them? Yep.
Plus 2 pi.
Yeah. So not the most professional math notation here, but I'm just going to go like that. Plus 2 pi m. Okay. And remember, always look for where the graph ends and starts, and if it's not at the same y value, like if it wouldn't connect, if you wrapped it around, imagine wrapping it around a cylinder, then you don't have, for a connected graph, you don't have one cycle. Connected graphs, always continuous graphs, have to start and stop at the same y value if you are showing one cycle on the screen. Any questions on that? All right, so let's try some inequalities. This is what we'll finish up with. Solving inequalities is the same as solving equations. You're still going to have to find roots, or you could do intersects if you want to, but we'll see what we do. So you're still going to solve it just like it was an equation, but just remember when you write your answer, what do answers to inequalities look like? It's not just like x equals 6. Answers to inequalities are generally what? Yep. Intervals, yes. It's like a range of values between 3.2 and 4.7, something like that. Yep, they're intervals. So we do have to pay attention to vertical asymptotes. Vertical asymptotes break intervals. So we have to deal with that. We also have to put proper brackets and parentheses. Okay, so let's try this one. Find where the sine is less than the cotangent. So let's leave it like that. Let's do this one as an intersect problem. So I'm going to put a y1 and a y2. I could do it as a root problem, just as easy. But let's do it as an intersect. What is the period of sine? Yep. 2 pi. What's the period of cotangent? Yeah, just pi. Okay. What's the least common multiple of 1 pi and 2 pi? Yeah. I know that one's come up a lot. It's not always going to be 1 pi and 2 pi. It's a pretty popular one, but could be something besides that. So whatever interval you find that is the solution in whatever cycle you're looking at, that interval that you find is going to repeat itself every 2 pi radians. Okay. So let's put in sine of x. Let's put in cotangent. Make sure we set our window. 0 to 2 pi, that looks good. And we're looking for where the sine is under the cotangent. All right, so let's look at that. First question, is the sine ever under the cotangent? Does that ever happen?
Yes, it is.
Yeah, it does go under the cotangent at different points. So it's under from here to here. Now remember what's happening here. That's a vertical asymptote. And the next part, this part right here, that's above the cotangent. Then when we get past the vertical asymptote, it's below again. So those are the two intervals where sine is under the cotangent. So we have to find what they are. And those two intervals that I just traced in green are going to repeat every cycle. So once we find them, we're going to put a plus 2 pi n. All right, so let's start with, we'll call that interval 1, interval 2. Let's start with interval 1. What's the left edge point, left x value of interval 1? Yeah? 0. Can I include 0 or not include 0? How come? What's that?
You can't include it.
I can?
Yeah.
I like I can't better. Let's go with that. So you can't include it. But my question is, how come?
There's no equal to sign.
That only comes into play when we start looking at where they cross each other. So we're going to worry about that here and here. The reason I can't include the 0 is because of that. There's a vertical asymptote there. If you try to include 0, that's undefined on the tangent, or cotangent, whatever, yeah, cotangent. So don't include 0. Now, this intersection point, am I allowed to include or not include? That's a not include. And that is because you have to be under the graph, not equal to it. So I need to find that intersection point, and whatever I get, it's a parenthesis. Now let's go to interval 2. Interval 2 is going to end right here. I'm going to have to find that intersect. I don't know what it is yet. And I know interval 2 is going to start at the asymptote, so I cannot include it. But I do need to know what that asymptote is. What is that asymptote? Yep.
Pi.
Pi. Yeah, it's not going to be a hard asymptote to find. I'm not going to give you one that's super tricky. It's right in the middle of 0 to 2 pi. So that's what I know so far. Okay. Now I need to find the intersection point. So let's do that. You've got to be a little bit careful because this curve is not continuous. So put your cursor, put it close to the one that you want, especially for the tangent one. Okay, so we get 0.90. That's where interval 1 ends. Now I got to see where interval 2 ends. Second calc intersect. That should be good enough. 5.38. And those two sections are going to repeat every cycle. So what would I want to add to each of those intervals? Yep.
Plus 2 pi n.
Yeah, and what that really means is you can add 2 pi n here and here, there and there. But the way I'm just going to do it is put plus 2 pi n on that whole interval, plus 2 pi n on that whole interval. And that's how you solve a trig inequality, graphically. Okay, let's look at this one. Let me just see what we have left. Okay, so 2 problems left. Let's do this one. And again, I'm going to leave it the way it was, leave it the way it is, just like I did in the last problem. Don't rearrange it to get 0 on one side. So it's sine 2x is greater than or equal to x squared minus 1. graph it. Sine 2x and x squared minus 1. So I'm looking for where the sine function is above or equal to the parabola. I'm going to hit graph. I'll just try my window. Nah, that's not going to be a good window. I'm only going to see half my parabola. So let's bring it back the other way. Let's do negative 2 pi. It's going to give me a symmetric picture. Okay, so there is my graph. Okay, is there any section where the sine function is above the parabola? None?
Yes.
Yeah, how many?
I think there's only one section right
Is-
after the first intersection.
Yeah, it's only one section, right? From here, and I'm using a closed circle because I can equal it, up to right there. Is that section going to repeat later in another cycle? Is that answer going to repeat in another cycle? No, why not? I thought with sine, like trig functions, you have to put like the period times n to make sure we get all the answers. Yeah. Yeah, the parabola doesn't repeat. So yeah, you're going to get that section again right there, but you're not getting the parabola again. So this is not a periodic solution. It's one section, and that's it. So all we have to do is find the two intersection points, and that's our answer. And we're going to use brackets because it did say we could equal. So we get negative 0.46. That's the lowest radian value you can pick. And the highest radian value is 1.26. If you pick any angles between those two values in radians, the sine curve will be above the parabola. If you pick anything else, it will be underneath. Any question on that one? All right, and the last one. So the last one is when you have a compound inequality. You have three parts: a left, a middle, and a right. Well, it doesn't really change how we do it. We're just going to plug in a y1, a y2, and a y3, and we're usually looking for where, the way I do it, where y2 is sandwiched between y1 and y3. Okay, so you're looking for where something is trapped between two things. All right, so let's try this one. We're looking for where x sine x is sandwiched between negative x and positive x. What kind of transformation is that when you multiply by a number in front of the function? Yep.
Vertical stretch.
Vertical stretch. And this is a variable. So what this problem has is a variable vertical stretch, meaning it's a vertical stretch that is constantly changing. The farther away you get from the axis, the more vertical stretch you have. As you get towards the origin, towards the y-axis, the vertical stretch basically goes down to 0. And there is no vertical stretch. So let's graph that. So I'm going to put negative x in y1. I'm going to put x sine x. I should have cleared it first. In y2. And I'm going to put positive x in y3. So we're going to look for where the variable vertical stretch graph, it's going to look like a sine wave that's growing as you move away from the y-axis, where that is sandwiched between my two lines with a slope of -1 and +1. And let's try zoom 7. So there's -x. Here's my sine function. We can't see much of it, so let's zoom out a little bit. So there's -x. There's my sine function with my variable vertical stretch. And there's +x. So let's just see if we can interpret what's going on here. I want to look at where this graph is above -x, that's the blue one, and where it's below +x, that's the black one. Where is the red graph above the blue but below the black? Yeah?
When it's greater than or equal to 0.
Yep. When x is greater than or equal to 0. I'm above the blue and I'm below the black. Now, let's finish up with this one. This one's going to look very similar as far as the picture. But because it's being graphed in color, you'll be able to see that it's not the same graph. So let's do negative absolute value of x. Middle one is the same. And positive absolute value of x. Now, if these two graphs were black and white, you wouldn't be able to see the difference between them. But they're in color, so you can. What's the difference? Yeah.
Are they sandwiched between each other?
Yeah, this is the whole time, right? You don't actually have V shapes being drawn in this graph on the right. You have two lines that when they intersect, it looks like a V shape, but the V shape is actually part of one graph and part of another graph. When you draw absolute values, you are actually drawing V shapes. Right? This blue is a V, and the black is a V. That is the same graph. But if you look at where we are above the blue and below the black this time, that's all real numbers. So all reals. Okay, so that's where the color on the calculator, it does come in a little bit handy. Otherwise, those two would look exactly the same. You just have to identify it by when you hit trace. You could always see which one is which. Right? So if I press trace and I'm on the blue graph, that tells me which one it is. But color does make it easier to see. Okay, so that is 7.3. So it's all graphic. Every problem we did today was graphing. Okay. I don't always think graphing is the best way to do it. If you have a really complicated problem you can't do algebra with, maybe it's a good way. But remember, graphing never gives you exact answers, and it can take longer depending on the problem. Something like this, there is no way I'm going to do a problem like that with graphing. That's just a waste. You can do it way faster with algebra. So when we get to 7.6, we will talk about some more equations we can do algebraically, mainly because we're going to want exact answers, not the decimals like we did today. All right. So that is the homework for tonight. So 5 to 7, 11, 15, and 29 to 31, those are all. But the 19 to 25 and the 33 to 37 is all. So again, make sure you do have access to your graphing calculator on your Chromebook, because you need that for almost every question.